Better. Okay. Sweet. Where were we? Okay. Yesterday we wrapped up type checking. It did manage to take all of class. So today we are going to start on talking about imperative kind of command-based programming. This is what you guys are a little bit more used to probably. That's like your Pythons, your Cs. You know, you program in a sequence of actions and then the computer executes those actions, right, in order. The functional programming we've been doing, you notice, doesn't really have any kind of sequencing, right? The closest thing we really have to that is like you have those let bindings and then they execute really before the next one. And we could actually talk a little bit about how that evaluates, but that's actually not always necessary. Sometimes you can actually work out of order as well. So what we've been doing so far doesn't really have any notion of like, do this, then do this, then do this. Hasn't really been present. It's kind of there because we have to make it do something first. But we could have actually done that kind of in reverse order, try and reduce everything maybe on the in part of a let, and then go and figure out what the variables are. We could have done that in a different order if we wanted to. For instance, today it's going to matter a lot more. We're going to add mutable state. We're going to add a whole bunch of constructs you guys are used to, variables in the more traditional sense, right? Ones that you can assign. Yeah, so, but before we jump into that, let's just talk logistics a little bit. So reminder, homework 4 is going to get an extension till Friday at midnight. I still need to put that extension in, so if you try and submit it right now, it'll probably say it's late, or it won't let you to submit. I will hopefully remember to do that after class. Today's quiz isn't online yet. I need to see how far along we get before I type up those questions, so expect that sometime pretty quick after class. There's something else. Homework 5 should go out tomorrow morning, not today. Took me a little longer to kind of get stuff done this morning. And I think that's it. Yeah, get started early on homework 5. Again, it shouldn't take you quite as long as homework 4, but it could. So I think that hits everything logistically. We have 2 weeks after this week. I've prepped new lectures for today and tomorrow on imperative programming, so they're a little bit different than how I've presented it in the past. So kind of bear with me as we kind of explore this material, because doing it a little differently this time around. So feedback would be awesome too as well. Otherwise, next 2 weeks after we finish imperative programming, that's when we get into kind of special topics. We can do a little bit more. In the past, we had done a project during this time. So there was some stuff lecturing around those projects and some in-class time to work on those. We're not doing those this semester, so we'll just hit some special topics, stuff that I wouldn't normally cover. Basically give me a chance to build out some new lectures. So that's kind of the game plan going forward. Otherwise, let's jump into the material. So first thing we should talk about is, does anyone know the difference between a pure and an impure program? Or can anyone take a guess at what those might mean? So yeah, so Markov says impure represents irrational numbers as terminating decimals. No. Arthur says impure means inexact, maybe. Not quite. So typically when we talk about pure or impure programs, what we talk about are impure programs are going to be programs that have side effects. So programs, languages, that have side effects. Now I've just done a very convenient thing for myself is I've kind of used, or I've defined this in terms of something that we don't know the meaning of. What's a side effect? Usually side effects will be something like mutable state. So that's a type of side effect. And remember, that's state where you can kind of change the value of different variables. So something more traditional, like a Python or C, where you're changing the value that exists at a variable as you execute a program. Exceptions are typically included in side effects. A whole bunch of other kind of things get lumped into the side effects. Typically, if there's like networking output even. So if you have output of a program, that's technically a side effect. A little bit different than like a function returning a result, but this would be like your program printing something to the screen, right? Because that's, if you think about it, when it prints the screen, it's affecting the state of what's on the screen. Even if you have a pure program, it producing an output does something impure in this weird kind of mental gymnastics kind of way. Whereas a pure program will, well, it doesn't use side effects. Or mutable state. Should be an A. And these are things, usually functional programs will be pure, usually, not always. And I think that the thing that might be most helpful for how to think about this is that things that have pure state, if you execute it, no matter where you execute it, under any circumstances, it always produces the same result. I think we had a good question in chat that I'm about to read. Yeah, and then the opposite of that for impure, right? So impure programs may not always produce the same result if you execute the same program. So you could think about it if, say, I wrote a program that works on, say, pointers in C, and you run that program, every once in a while, you may not get the result you expect. And that's maybe because you didn't clear the memory out. You didn't set, your null. You didn't like clear out the data that was there, maybe, if it wasn't like a clean memory allocation. You could also maybe hit some kind of like memory overflow, in which case you would probably still get a result, but it would just be nonsense because it's like bumping into memory that you're not supposed to have access to. Whole bunch of problems can come up in an impure environment, right? Couple of questions, or there was one question so far, now two questions in chat. Markov asks, would a RESTful API be impure or no? So strictly speaking, a RESTful API would not be pure. And that's because you're using state transformations inside a REST-based API. I wish I could remember what REST stands for too. That's really bad. I should know. Wow, I haven't done any kind of networking stuff in too long. This is bad. But yeah, a RESTful API would definitely be impure. That being said, though, you can definitely get pure fragments of it. So if you're just getting data and that data is for sure not going to change, that would be kind of a pure fragment if, say, you froze whatever data you're trying to access. Yeah, representational state transfer. That sounds right. Yeah, so if that state changed at all, it would create an impurity, right? Because you're dealing with state. So generally speaking, if there's any state that could change at any time without you directly changing it, or even with you directly changing it even, it's probably going to be impure. Another one was, what counts as a side effect in this case? If a program does multiple things, does that make it impure automatically? Arthur, can you elaborate just a little bit? So doing multiple things isn't per se going to create impurities. But if, for instance, you have like a multi-threading situation where you're doing more than one thing at once, if you have threads, it's impure, I think, is a general rule. There might be an argument, people that do kind of multi-threaded synchronous and asynchronous concurrent programming could argue that there are probably pure fragments of multi-threaded programming, but on its own, probably not pure. So if it's thread safe, it may be pure. I'm not sure if it would always be pure. Only because even with thread safe programs, sometimes the mechanism for threading can still create impurities. So typically, it depends how threads are implemented. If threads are implemented at the language level, it could be pure, I believe. Working this from first principles, so I have no actual concrete experience here with this, but I would assume if it was thread safe in the language level, it could be pure, not necessarily, but could be pure. And if it is implemented with the operating system, which is typically how threads are implemented, it would definitely not be. There's a whole bunch of ways those can fail. So Pseudo asks, I can see a lot of examples of impure. What's an example of a pure program? So everything basically we've written up in this class up till now, it has been pure, right? So if you think about it, when you run your Scala notebooks, say you ran your interpreter for our language so far, you would never expect for 5 plus x to give you anything but 5 plus whatever x was defined as. X is going to be fixed, right? But in an impure program, say with a loop, that x could change as you go. And because that x is changing, we've introduced impurities, mutable state into our program. And if you affect x, that's a side effect, right? If I do say x equals x plus 5, right? That's changing that x and updating it. So it's not a fixed x anymore. And so when you run that program multiple times, it's going to be a little different, right? And if x wasn't reinitialized, it's going to be way different. Yeah, so Pseudo says, or asks, so we're slowly going into impurity. Right on. We're going to start just basically introducing it today. We haven't had impure programs yet, unless you kind of cheated on a homework problem, used a loop at some point, which hopefully you haven't done. It's possible, but I doubt it. Some of those problems would be hard to do with loops. Ooh, Arthur asks a very good question. So if loops are impure, how can functions we've written be pure, since we've used so many recursive loops? Very good question. So recursion is not a loop. So note that with recursion, we only ever refer to the input values. We don't ever actually change state. So for instance, we've never had to keep track of, say, an extra kind of sheet of paper that has a bunch of variables on it that could change. If we had x maps to 5, we're never going to cross out that 5 and put 6. What we would do is we'd add, if x for some reason was shadowed, which is allowed, we would have a new x that shadows it, pointing to 6. Now that seems like the same thing. It's definitely not. Okay, it behaves radically different, especially when you start introducing functions into the mix.
So it's like a child of the original x?
Here, it's not really. It's actually saying, okay, when I go and try and retrieve an x, I go from the bottom up to the, it's accessed like a stack, right? Whereas mutable state, so I'll put execution environment here, whereas something like mutable state would actually have x maps to 5, but then maybe if I did an update, I'd just cross out the 5 and put a 6. Like the 5 is unretrievable. Here, the 5 is actually always there. It's just farther up in the store. And so why this matters is that if you remember when we started doing let bindings, the let was scoped to the in part. And so you could actually drop out of the scope, and that this X maps to 6 might fall off and might disappear. So the example would be some program like this. If I had like let Y equal let X equal 5, I guess I could have a let Z equal, or no, I'd actually want another let X. If I had let X equal 5 here, and then let X equal 6 here in X plus X, and then say in X plus Y. This X, I'll color code this. This X refers to this X, whereas this refers to those X's, right? And so when we pop back out of the scope, that X maps to 6 is forgotten forever, right? And there's this scoping thing that's happening as well. Well, mutable state will also have a notion of scoping, but it's going to allow us to do loops in the way we're used to. It's going to keep that data around until we exit a block of code where it was declared for the scope. The examples I'll show you here in a second will make this a lot more clear. So, yeah, and Markov says chicken meets egg because the environment is changing every time a new expression is evaluated. It seems like, you know, there's a chicken and the egg problem going on, and there sort of is here. With some examples, I think the difference will definitely start to pop out, especially when I show you a loop. It'll be really clear why these two are different. So we're going to be really careful about separating impure and pure computations with Lattice. We are going to introduce this new language feature inside the Lattice language that we already have. So we'll be careful to separate the impure parts of Lattice from the pure ones. And we'll do this, because of the way we do this, we're basically going to keep around all the expressions that we've defined so far. So we don't need to redefine like arithmetic and stuff. We already have that. They work well. So we don't want to have to do any more work. We just want to create a fragment inside our language that's impure, and it's going to give us all those features. So let's actually take a look at, oh, we had another question. Yeah, so the question from Arthur is, am I correct in assuming that the main difference here is that recursion has multiple instances of the same program as the loop operates, while a conventional loop instead overwrites the same instance? I think as you've framed the question, yes, you are correct. I don't like using, yeah, so thank you for putting that first loop in quotes, because it's when we do recurrences, it's not looping at all. It's actually calling a function with different arguments, which effectively we can think of it as a loop, and it's equivalent to loops in certain ways. But recursion isn't as good with mutable state at all. Like using mutable state in recursion is really weird. So we just use a different mechanism for affecting changes in there. And there's a place where you would want to use loops over recursion and vice versa. So like for all the programming we've done up till now, recursion makes a lot of sense. It's because all these things look really like they make almost semantic sense as recursive loops. It's like I need to evaluate plus, and it has 2 sub-expressions. You know, do you want to evaluate those in a loop? That doesn't really, you'd have to like introduce a stack to like, you know, what you still need to evaluate. It just get really weird. Doesn't really work. So recursion actually just makes sense there. It's like, okay, well, I need to evaluate this, make a recursive call, right? Whereas a loop would be better for actually manipulating memory, right? It's like, okay, I don't want to recur through memory. It doesn't work. I can just loop through it. You know, it's like, I just want to move down the list, right? something like that. So, okay, let's jump into the actual kind of syntax we're going to introduce. So I'm going to introduce a few when I get the tip on my pen screwed back in. Let's just start with some example programs, and then we'll work into the syntax from the examples. So example 1. So this is our first sample program, and I need to be careful here. So I'm going to introduce now the curly brace into our concrete syntax. This is going to introduce a new expression that allows us to have an NPure program. So we can embed this into a regular old expression. And don't worry about that quite yet. We'll get to that kind of example, but just know the curly braces mean a really specific thing here. So new curly brace, and then here we'll have new A, and then we'll assign A the value 0 in new B is true in while the value at B is true. Do this block. And the inner block will be A will get reassigned to A, or the value of A plus 1. B will be the value of A is less than or equal to 5. Close the while block. And now we see our first semicolon we've ever used. Oh, I lied. There should be a semicolon here too. And then return A. And then we'll close out that last block. Can anyone kind of sum up in plain English what this program does? Definitely doesn't look anything like the Lattice program so far. There's a couple things that are kind of carried over, the addition there, less than or equals to, that's still around.
Just adds 1 to A until A is 5. Yeah.
Right, yeah. It's just looping and adding 1 to A until A is greater than 5, which means it'll be equal to 5, right? Now, what if I change this program? Oh, wait, that's my second example program. I don't want to get to that one yet. Cool. Anyone unclear on what's going on here? Hopefully it's a pretty easy program to read. I do want to point out here we're allocating new memory. So these new blocks, what color do I want to use to annotate this? This is memory allocation. It's not like a malloc kind of allocation, right? We don't have pointers here per se. We still use kind of a dereference thing here, but that's just a mechanism we have kind of for the sake of it. I don't have a better answer than that for now. Yeah, but we have allocation. It's useful. We probably don't need it, but we use it to kind of keep our scope really clear. So note this has a similar thing to let, where we have an in at the end. So it's kind of like this whole block is contained inside kind of this semantic construct, which is contained inside of this one. So we can see that same building up that we've kind of been encountering all semester. Yeah, and then at A gives the value stored at A. Or at location A. Can anyone tell me what return does here?
The value at A.
Yeah, so it returns, basically it says this whole block will return whatever was at A, right? And I suppose that ought to say at A, I think. Yeah, it should say at A. I might forget to throw my little ats in there, so call me out if I do forget. Like I said, there is a reason for that at being there. Maddie.
Is there a reason for like the semicolons?
Where I've put it, because it's weird. I kind of only put semicolons in some like certain places, right? So the semicolon here doesn't necessarily mean like I'm done with a line. Semicolon here actually means I'm sequencing actions. So I'll write that down. They're sequencing of commands if I want to keep my language straight. So we only need it where basically I want to do 2 commands, but where I only need 1, if that makes sense. When I actually give you the formal syntax, it'll make a little bit more sense where I've put them. But I have been very deliberate about where I put my semicolons here. It's actually kind of interesting because I think a lot of the time we use semicolons in programming, we actually don't need them, which is an interesting little problem. I guess Python doesn't have them, but like in C, there are times when there's a semicolon that I think strictly speaking, there need not be one. For instance, at the end of like a for loop, you strictly speaking don't need a semicolon for reasons of parsing. Because you're always going to have a closing block there. And I believe, and correct me if I'm wrong, it's been a while since I've programmed C, but you would usually put a semicolon after a for loop.
I think only after like structs and classes.
Oh, maybe it's only,
Is when you put,
oh,
like,
okay.
a semicolon after a bracket.
Mm-hmm. So maybe not. So maybe not then. But I'm not sure. Either way, you definitely don't need it. Semicolons are really just used for parsing. Here, we need it to actually delineate sequencing, which gets dealt with in parsing, right? And then it turns it into a different notation, right? So yeah, there's a reason why I've been deliberate about where I've put those. Good question. Yeah, that'll get cleared up here in a second when we start defining the syntax. It is the way I've programmed this is really weird. Why not just use A? That's a pretty good question. It'll be clear in a second why. I think that's all I want to point out here for now. Are there any other questions before we jump into, I think actually the syntax. I don't know if I want to, oh yeah, I actually know what I'll do next. Before we do the syntax. So something else we can do with this program is we can embed this in a lettuce program. So example 2, which is really just an extension of the first example. We can embed, and I'll call these imperative blocks, probably imperative blocks, inside regular lettuce programs. So what do I mean by this? I think I was using white above. Let's use the same color. Cool. So I could have something like let x equal, and then take this block and copy it over. Equal that whole big thing in x plus x. What does this compute to? 12. Try again. I think you're just up by 1. You're really close, just to be clear. should be 10. So X is going to be 5 after we've executed this loop, right? Is everyone with me there? Or did I?
Yeah, I thought we were saying 6 because it's like it only does it once A is greater than.
This is why imperative programs are bad, because they're hard to work out. So we do while B0 plus 1, and then we do the check. So then it would be false. Yes, you're right. It would be 12. Good catch. So it would do it one more time because it's less than or equal to. I should have just had that be less than, right? If I wanted to do that. So good catch. Yeah. So this will be 12. Bonus points for Conlon today. Right. So we can embed these inside Lattice programs, but notice that we've clearly separated the two. We've kept the impure separated from the pure. So question for Markov, how is A not a pointer and X not a lambda? I won't get into why X isn't a lambda yet, because you know what a lambda is, and we haven't, or I guess we have talked about lambdas in class, haven't we? We have talked about that a bit. So X isn't a lambda. I won't get into why until probably next week. We can bring that part up later. I'm not quite sure where you're going with that part. Why is A not a pointer? Because we don't have any kind of, so I guess strictly speaking, A is sort of a pointer, but there's no memory address that we're getting. So you don't have some kind of like hashed, I guess they're not always hashed, but some like nasty looking 8-bit memory address. You don't have access to that, right? So this isn't in the heap, right? This is just like, I have memory, I have access to memory, but where that memory is, I don't have access to. So calling it a pointer isn't quite precise. I guess you could call it a pointer. It wouldn't quite be wrong, but we don't have what we would typically associate with pointers, like pointer arithmetic and stuff like that. So that's why I'm being careful with that language, because usually pointer comes with a whole lot of other stuff. Here we just have addresses. And I want to be really clear about that part. So hopefully that clears that up, Markov. If not, elaborate a little bit in chat, and I'm happy to pick that back up. Cool. So this is to point out these blocks of code are sort of expressions, but they're expressions in a very specific kind of way. So for instance, I couldn't put just like new A equals 0. Can't do that, right? Why can't I do that? Well, it doesn't return a result. So we're going to require, this is going to have to return a result. It might not always. So this is also a place where a program could like have problems, right? We could have an infinite loop. Infinite loops, not pure. Actually, infinite loops might, I think it depends on our definition of purity. Infinite loops usually aren't considered pure because they're non-total. Anyway, I'll have to look that up. I'm sure there's a distinction there. Anyway, let's start talking about the actual syntax of these, kind of concrete, abstract, and define it as a grammar. So let's start with, we'll just say extending Lattice. So if we remember from yesterday, I said that when we have a new language construct, we have to kind of update all these blue parts, right? So we have kind of type checking. We'll need update type checking. We have the operational semantics. We'll have to update those. We'll also be introducing a little bit of a new semantics to actually handle the impure parts. And then we'll also have to create new concrete and abstract syntax. So let's start with the syntax piece. We won't get to the semantics until tomorrow. What should I change about our syntax? What's probably the entry point for dealing with this? What could I add? Or what should I really add to, I guess, to get started?
Like the brackets. Curly
Brackets.
braces.
Yeah, like that curly brace construct, right? That allows me to put a set of commands inside an expression, right? So we're going to extend expression, right? So we have expr, and expr is everything we've used so far. So I'll just kind of put the ellipses there to represent that. And then we'll also introduce a new construct called block. And block will take a single argument, and that argument will be of type command. Have we defined command yet? Probably what we're going to do next, right? Conlin's shaking his head. He's like, yeah, participation points. I can nod my head. That makes the teacher happy. Okay, so let's start talking about command. I'm going to have you guys try and define as much of this on your own with my help as you can. So let's go back up to our example and let's try and pick out all the new stuff that's happening. So in this example, what are the new constructs that are inside the command? So command, the stuff that's kind of eligible will be anything here, right? Or I guess I can. Ooh, that's neat. Okay. So anything in that kind of yellow and orange box.
New.
Yeah, so that new construct is different, right? So the new block that we've used is this whole thing, okay? That's the whole kind of concrete syntax. So we will call this a new variable declaration or a new state declaration, right? So we'll call this decal. And then what should declaration take if we look up here? I'm going to change the color of this box though. That's better. Now I can use my highlighter again. That's the eraser, highlighter. So we're looking at this part. What other arguments are we giving? You know, what parts of that are kind of syntax? What are other arguments that we're going to kind of give to the syntax? Or what?
String and a value.
So a string and a value, right? So maybe not a value, right? Because we don't usually have values in our programs. Instead, we should have an expert. We want an expression, right? Right? Yeah, I knew what you meant. So we want a string, and we want an expression. And then just like let bindings, we also have that in. So it's really actually in the same construct. We also have all of this stuff, but it's kind of nested inside. So what should we put there?
Just a quick question.
Yes.
Is the like semicolon equals different from the two semicolons?
It is. So notice that the two colons, right? The two colons equals we've only used talking about grammars. That usually means you have a new kind of mathematical definition, or what we would call a judgmental equality, which you guys don't need to know what judgmental equality is. Although math guys, you probably would be interested in the difference between judgmental equality and other stuff. Colon equals means a new assignment. So we're assigning a new value. Whereas here, even when we use this, you don't usually use it to say I'm like reasserting what expression is. It's really, you only ever use this one time. Whereas each time you use colon equals, it's kind of doing a new assignment, if that makes sense. So good question. Yeah, so pseudo is like kind of like X's rest of the program, like a list of more commands. Right on, I like that. So this part here is going to be more commands. It won't be a list of commands. And the reason for that is because we're going to introduce something else that will allow us to build up lists of commands in a second. So we won't quite build a list. We could do a list, but we won't, because it introduces some more complexity than we actually need here. So, but yeah, pseudo, right on. So we're going to have here at the end also command, which will be kind of the rest of the program. In a second, I'll write a nice big chart about the difference, the concrete syntax versus the abstract too. So we'll get another look at this in a little bit of a different view, kind of like that green stuff as we were doing type checking that I started writing. Great, awesome. Okay, what are the other constructs that we have up here that are new? I just really want to delete the orange. I know how I can do that. I need to highlight the orange. Cut. That didn't do it either. I'll just re-highlight. Cool. So what else up here do we need to add to command? So Markov says return and while. So let's start with return. What ought return take? So it'll definitely be called ret. Should we spell it? No, all of these are like 3 or 4 letters. So yeah, we'll leave it at just ret. Pseudo says a value, but Ron says maybe not a value. What should it be, Aaron? An expression, right? So we don't ever want a value inside our program as we write it. The values are going to kind of come out of the execution, right? But yeah, pseudo, I think you're on the right track for sure. Sweet. Okay, so and then also Markov said while loop. So let's do while. What ought while take? So let's pop up here and take a look at it. So the while block, I'll highlight the part that kind of constitutes the while block. It's this orange shaded part. Or maybe this orange shaded part. So up to that semicolon, but not including that semicolon. What arguments is that going to take? It's actually quite a bit simpler than kind of what's highlighted.
All right, an expert first for the condition.
An expression for the condition? Maybe.
That is a value this time, right? Since the value at B.
Well, it's going to get a value, which is an expression. It's some gymnastics here, actually. So the at B is actually not going to be, and I guess you wouldn't necessarily know this yet. We're actually going to put a command there, not an expression. And the reason for that, I was thinking about it earlier today. I couldn't quite come up with why exactly that is. A lot of this lecture is coming from a graduate level textbook. They didn't talk about why they put a command there versus an expression. It probably matters. Oh, I think I know why. Yes, I think I know why. But I'm not sure. I want to double check. But we'll put a command there for now. That has some extra utility in that we can have kind of an embedded program. And it will require us to do this weird kind of at B stuff. We won't be able to directly embed the check there. We'll have to put a variable there. And I'll try and get a better answer for tomorrow. I thought I'd come up with it during the day, but I couldn't. So we'll put a command for the condition. And then what about the rest? Another command? Yeah, another command. I like it. So while just has 2 commands. Sweet. So I think I figured out how I can get rid of just the orange highlighting now. Yeah, that did the trick. Now, what else don't we have constructs for? So we've kind of knocked out declarations of new variables. We've knocked out return. We've knocked out while. What else is up here that we don't have syntax for yet? There's one really obvious one. Maybe 2 really obvious ones.
It's like the semicolons.
The semicolons, right? Sequencing. What do we think those take? So these are like really deeply embedded, so it might be kind of hard to tell. But let's give it a try at least. If not, then I can kind of give the answer. So sequencing, what do we think it takes? So here I have a command there. Let's keep using the highlighter. It's easier to tell. I have a command here. Nope, that's the eraser. command there, and I have another command there, semicolons in the middle of the two. So what do you think sequencing takes?
It's 2 commands.
2 commands, right? So it says do one command, then do the next command, right? So you could kind of think of this, if I get my little highlighter out, you could, that's the first one you're doing, this is the second one, right? Just do them in order, right? And those can be really complex programs, and that's okay, right? So that's all we're doing, is we're just sequencing. So 2 commands there. And ironically, you guys chose to knock out all the hard ones first, because the 2 easiest constructs here, you guys haven't touched yet, which is, I find, quite interesting. What else do we have to do in yellow? At, yeah. So we would, in C, we would call this dereferencing. We'll call this get. Okay, what should that take? We'll call it get. What ought get take?
String, right?
Yeah, just a string. It's just going to be pointing to some assignable that we've already created. I'll use the word assignable too for variable instead of variable, because variable has this really overloaded meaning. We'll say assignables here. So that just takes a string. Markov says new. We've already done new. That was the decal up here. And then what else? We have one more construct that we've introduced here in the yellow. And it might hide from you because some of the notation here is, you might notice, is reused.
That colon equals.
Colon equals, yeah. So notice that we use colon equals in 2 places. So the first being here with new declarations. Oh, I still have the small highlighter. So we have these new declarations, right? Those are one use of the colon equals, but then we have kind of the more normal use where we're reassigning a value, right? So something's already been declared and we need to kind of update it, right? So these are things that are already in scope. What should those take? So we'll call that set, right? Because it's setting a value. What should that take, do we think? Keep Conlon from looking at my nose. That's how he's on top of things all the time, I bet. Any guesses? Oh, Pseudo, were you answering this question? I think you're right. If you were answering that question, I think you were. So set should take a string, the address, right? So the assignable. And then what else can it take? Yeah, so this is the interesting part. Should it take a command here? What else could it take? We have some options here. And to be honest, I'm not entirely, yeah, Pseudo jumped in and says expression, should take an expression. I'm partial towards putting an expression here, right? So the plus is the thing on the outside, but I'm seeing a lot of squinty faces in class. No, just one really. Aaron's really giving me some like eyes right now. He's like, I am confused. Yeah, and Arthur just pointed out, can an expression contain an at? This is a good question, can it? So now we hit a little problem. We're gonna have to be careful when we start defining the semantics tomorrow. And I put this off until tonight, so I haven't written this lecture yet. Reworking this stuff, like I mentioned. We will have to figure out how to deal with that. So one way of dealing with this is we could, if we're allowed to keep our mutable state around, and it's allowed to kind of like stay in the inner blocks, what we could do is create a new block here where that block is an expression. And so we're kind of like encapsulating that command inside an expression, kind of nested inside a set of commands. It's not the prettiest way of doing it, but we can make it work. The other way would be to figure out a way of making expressions part of the command language. which would be acceptable as well. But I don't love that either. And that's because we would need to introduce some way of having dereferenced variables inside of expressions. And that muddies the waters now. So what we'll do is we'll actually say, okay, well, when we encounter one of these inside an expression, we'll assume there are blocks inside. Okay. And more on this tomorrow. I still need to decide what kind of makes most sense. I think this is going to be the one that kind of makes best sense and will be cleanest. Either one kind of works as long as your semantics, are consistent with that. I think this version will produce the better semantics. I won't know till tomorrow though. So you guys are kind of along for the ride right now.
So then is that a command inside of an expression? If you do it that way?
That would be a command inside an expression. It would be a new block, like from here, right? Inside of plus, right? Because the plus would be the overarching constructor there. So it's kind of weird, and we're gonna have to be, when we do that rule, these rules, we're gonna have to be really careful about passing the state along to the expressions. And I don't know if I like how this is gonna work yet. So it could be possible I don't like how this works, and I update this a little bit tomorrow. We'll play with it. We'll see what kind of works. So yeah, and Arthur asks, can an expression contain the at? It's like, well, kind of, by containing a command that has an at, right? Because that's allowed in our syntax right now. We don't have to do any extensions. If we wanted to add a dereference as a construct and expression, we would have to create new syntax and expressions. And that would also introduce impurities into the expression language, which I'm not in love with. We could probably do better there. Or it kind of muddies that separation, right? Even using a command introduces impurities into the pure language, but it keeps them separated, right? This would kind of have this cross dependency that I don't really like. So we'll try and stay away from that. More on that tomorrow, though. Tsudo, you asked why we don't create an address class inside, or constructor inside of command. We do have one inside of command. So that would be the get, right? That's what's referring to addresses, right? Or pulling the value. I think that's what you were talking about. So yeah, and to clear just that point up, so now we've done kind of all of the constructs there. There's 6 new constructs. That's the most we've ever done in a day, I think. So this is a big day for us, right? Let's just talk about the concrete syntax and kind of go between these two. So create a nice table for you just to make it more clear what each of these do. And great work, guys, deriving those. That was actually really good work as a class. I do appreciate that. Okay, so we have, I'm going to try my best to create a nice big old table here. And I'm sure it won't end up looking so pretty on the iPad, but I'm going to try my darndest to make this thing look nice. For those of you that don't know what darndest means, it's a thing we say in the Midwest when it's, I guess, an expletive, right? That'd be an expletive.
Is it? Like,
Think
I know
so.
you're doing your darndest, but like.
I appreciate you. Okay, so let's start with return. So return's kind of the thing that returns values, right? So we'll do too big. I'm going to move those over. You guys don't necessarily have to. So I'm going to put abstract on the left side, the concrete stuff on the right side. So we have return. So it's, said I was going to try and keep this as clean as possible. So I'm going to put there, return expr is the form. And I'm going to try my best to draw a dotted line here. And the concrete syntax is going to be return some E. So this side we have the abstract. this side, we have the concrete. Hopefully this makes kind of mapping the two a little less confusing, because I know a lot of people are like, wait, have we defined this yet? Have we defined this yet? Because they have different names in the abstract syntax. So it's more pronounced here than ever before. So then we also had declaring new variables. So we had decal, which takes a string, an expr, and a command. And the concrete syntax for this was new A is just the kind of the example address we'll use, is assign some expression E in some command C. Or I'll even put in command. We'll have get. Get just takes a string. And this is that at and A. We'll also have set. Set takes a string and an expression. And this will be something like A colon equals E. Hopefully I'm not going too fast. Everyone kind of keeping up okay? Sweet. Any questions so far? All good. Pseudo, thank you. Thank you for the feedback. Sweet. Then we have sequences, which takes two commands. And this will be something like command 1, semicolon, command 2. And our last one's going to be those while loops. So while, we'll take a command and a command. This will look like this. It'll be while command 1, that's the condition, command 2. And through sequencing, we can make those both longer too. Probably would break those into more lines than just that as well. Get that semicolon on another line, but I was running out of room. So that table looks nice. Hopefully this is helpful for everybody. So these are keep this handy for sure too, as we start defining semantics tomorrow. It'll be helpful. So let's see what else to touch on. I have one more example I want to go over, and I think we'll break for the day. So I guess we're getting towards time. So one more example of a program, which I guess I should have probably, oh, I lied. I think I want to show two more programs. So this is going to be example 3. And this is just to kind of give you guys more of a feel with the semantics now. So that kind of got our syntax out of the way, right? Those other 2 examples gave us a little bit of an impression of how the language is going to work. Now let's start talking about the kind of semantic details, right? Because there are some details and there's some weird corner cases. So this first is going to be a nice little feature of the language, or this extension. And blocks will be allowed to refer to variables in the environment. And I mean sigma here. So like the environment as we've been using it, right? So later when we start doing mutable state semantics tomorrow, we're going to introduce a new state, a new store for the state. We'll call it mu, so more Greek letters. it's going to be completely separate from Sigma. Okay, so it'll have different behavior. It's not going to be the same. We'll keep those two environments different from each other. Okay, so we'll have a store, we'll have an environment. More on that later. So we don't need to bog ourselves down with that detail yet. But basically what this little block of blue says is that programs like this will be allowed. So I could have something like let x equal 5 in let y equal block new a equals 0 in new b equals a is less than or equal to x. Someone turned in their homework late, but it's not actually late. That's what that email was, I think. I don't care if you do your homework in class. If you're in the online section, if you're in the in-person section, you have to write on paper. So class is recorded, so it's not a big deal for me. While at B, A is reassigned to at A plus 2, semicolon, B is equal to, at A. At A is less than or equal to X. Close brace, return A. Another close brace for the whole block, and then in, say, y plus 2. So we're allowed to, the big thing to point out here is we have x defined up here, right? We also refer to x here. That's allowed. Okay, so we can refer to our environment. I wrote out that big long example basically to show you can refer to x. The x's that are referred to here are allowed.
What happens if you were to like, instead of saying new B, say new X, and then like define a new
Very
X
good question. So how would we deal with that? You guys actually have everything you need to answer that question already. What if I referred to x? If I had like a new x there, so like maybe I'll write that out. So say I have like new x equals 5. Oh wait, it's already 5. Let's say 10. What would happen?
Just go back to that one, the new one.
No, it wouldn't. Why not? Why not? Any ideas? Now, maybe this is going to give it away. But if I put that there, then what would it be? When I put that at in front of the x, it's going to refer to the x from the mutable state. It's saying I have an address x, go find its value, versus a variable x. So this is that difference that I said, we're keeping them separate. That's why we have to have the at. Is it's going to do, like, we don't have to have it. We could definitely have it where the namespace is kind of all for free and loose and stuff, but then we run into that problem. So by having the at, we can actually not have to worry about keeping those namespaces clean. And that's a big, nasty problem that, trust me, language designers have had to deal with. And there's not a good solution to it. Not one that's like nice and clean. We don't want to mess with it. Maddie.
I know you already explained this, but can you explain again how it's not a pointer?
Yeah, it's more of a nuanced kind of technical point. You can think of it as a pointer for most purposes. The reason it's not a pointer, strictly speaking, is you can't do pointer arithmetic on it. So I can't go and like index it by 1. Like I couldn't create, using what we have here, I couldn't create, say, like a linked list, right? There's not that kind of like, you can't like store a pointer. Like pointers have this kind of first class feature to them where they can be passed around and worked with. Here, you can't actually pass, I need to be careful because you can pass the address around. But when you pass the address around, it's updating the address. but you can't like do stuff to the address. So it has some of the behaviors of a pointer, but not all of them. So that's why I'm not calling them a pointer per se. We have the at there to keep this namespaces separate more than anything else. It's not really don't really think of it as a dereference. It's really more of a get, which again, those are kind of the same thing, but again, not quite, right? So maybe when we go over the semantics, it'll be more clear. It also might not be. So yeah, bear with me there. Hopefully tomorrow when we talk about the semantics, it'll be like really clear why, those are different. So yeah, so just note, like with that X example, it's referring to the one from the environment, and that's because it doesn't have that ampersand, not ampersand. What's the at symbol called? It has a fancy name. I don't
And
remember.
did you just get it?
Ampersand? No, this is an
Oh,
that's an ampersand.
you're right.
It's and, yeah. Yeah, if anyone knows what the name of the at symbol is, I'd be curious to know. Plus A1 does what? Plus A1. Wait, where's plus A1?
It's not on there, but say we were to give a call to the plus function passing A and not the dereferenced A. Would it
So something like that.
Yeah, something. Well, I guess if you took the at symbol away from the line above that.
Yeah, that one.
Yeah, right. Something akin to like pointer arithmetic.
Yes. So yeah, so we won't. This will be undefined behavior, mostly because strictly speaking, remember this is an expression. That's a variable. So this would actually be a non-well-formed expression. So this would be treated like a variable, like X would be up here, or Y, that are just pointing to the environment, right? So it's kind of the same answer in some respect. Now, if I did have an A out here, then it would be 10, right? It wouldn't be referring to this A, it would be referring to this A. That's why the at symbol is really important here. Does that clear that up?
Yep.
Okay, cool, perfect. And again, when we go over the semantics tomorrow, when we actually give it a rule, the mechanism for doing this will become clear, and it'll be really obvious why that is, right? Right now, we're kind of shooting from the hip. I'm telling you how it works, so then we can define the rules tomorrow. Okay, one more example, then we'll get out of here. We're just about at time, so I'm going to do this really fast. So let's do example 4. Will this program execute properly? And the program is let y equal new a, assign it to the value 2, in return at a plus 4. Close block, in at a. What do we think? Is this a good program? Are we allowed to write that?
Like, no.
Conlon's saying no. Why do you think so? Other than it was a leading question.
Probably because the at A, it's sort of out of scope
Yeah, so
on the very end.
right on. I couldn't have said it better myself. So this is out of scope. It's not precisely because we're putting a command where an expression is, right? Because I could put, if I were writing this a little bit more syntactically correct, I would put a block there, right? But the scope from this imperative program has already gotten thrown out. We aren't keeping it around. So we're not allowed to have like a mutable state that refers to some other block, right? We can sort of mimic that with functions. So like functions play a role here. And we'll probably pull those examples out tomorrow because you could imagine passing addresses around. All that stuff's going to be possible. Or I guess passing addresses. Well, yeah, this is an expression where we're going to need a value for it, right? So this is going to get kind of interesting here in a minute, right? So we will Oh, are we missing a semicolon after the final? I don't think we're missing a semicolon here. No, because there's no sequencing in this one, right? So after this one, there's nothing else that comes after it. And then same for here. So no semicolon there because the semicolon just sequences two actions. So you need another command to need the semicolon. That's why semicolons here behave a little differently than how you guys are probably used to. But anyway, we're a little over time. So thanks, guys. We'll pick up again tomorrow with some of the semantics, probably a few more examples showing you how functions interact here. Otherwise, have a great evening. Yeah, good class today. That was enjoyable.
Thank you.